Today, I'm going to be introducing integration by substitution. So, to review, we have seen the definite integral of f of x dx from x equals a to x equals b, and one of the ways we can compute an integral like this is to find an antiderivative of f of x, which we'll denote as capital F of x, and you take that antiderivative and evaluate it at b and at a and subtract. And the number that you obtain from this computation represents the area under the curve f of x from x equals a to x equals b. Now we have also seen the indefinite integral of f of x dx. And so when you see an integral like this, where there are no limits of integration, you're just being asked to find the most general antiderivative of f, which we would write as capital F of x plus c. And so you can see that in either case, one of the key steps for computing many integrals is finding an antiderivative of the function you are integrating. And so we've learned a lot of simple antiderivative rules that are based on just reversing derivative rules that we've seen before. However, one of the difficulties here is that not every function has a simple antiderivative. Okay? Like, for instance, suppose you are asked to compute the indefinite integral of sine cubed of x times cosine of x dx. We don't have a simple antiderivative rule for sine cubed of x times cosine of x, and that is where integration by substitution comes in. It is a technique that allows us to find antiderivatives of more complicated functions like this one here. So the very first step when you integrate via substitution is you have to introduce a new variable, u. Now, for this problem, I'm going to let u be equal to sine of x. And as we go through more examples, we'll start to develop some guidelines for what to choose for u when you're integrating with substitution. So, well, if u is equal to sine of x, that means that the derivative of u with respect to x is cosine of x. Now, there's a little bit of ambiguity about the next step here. I've been mentioning many times that du over dx is not a fraction. It's a function. It represents the derivative of the function u. However, one of the virtues of the notation that we're using is that you can treat this expression like it's a fraction. So I'm going to write du equals cosine of x dx. So next, I'm going to take the equation here up top, as well as this equation down here, and I'm going to substitute them both into the integral I started with. So when one does that, well, this sine cubed, because sine of x is equal to u, we'll write u cubed instead of sine of x cubed. Also, cosine of x dx, I will replace with du. Now, we see here the power of integration by substitution. We started off with an integral where there isn't an obvious antiderivative rule that we can use for this function. However, after introducing a new variable u and making a substitution, we've obtained this new integral. And this new integral, we do know how to solve with those simple antiderivative rules we've learned already. The antiderivative of u cubed is u to the fourth over 4 plus c. Now, this is not our final answer. The variable in the integral we started with is x, and so we would like our final answer to also be in terms of x. And so you just have to replace u with, well, sine of x. And so the final answer would be sine to the fourth of x over 4 plus c. Now remember, whenever you have a function that is supposed to be the antiderivative of another function, you can check to see if the answer is correct by differentiating this function and seeing if you obtain sine cubed of x times cosine of x. So let's do that. Let's apply the derivative operator to the function sine to the fourth of x over 4 plus c. Well, the 4 in the denominator is a constant. It's not going to affect the differentiation. And so we apply the chain rule to differentiate sine to the 4th of x, which gives us 4 times sine cubed of x multiplied by cosine of x, divided by that 4 from the denominator. And the derivative of the constant c is 0. So we can cancel the 4's and obtain sine cubed of x times cosine of x, which is the function that we were trying to integrate at the start. So this verifies that the final answer that we obtained is indeed the correct answer.